Good evening, dear students. Today we are going to discuss maxima minima. That is one topic of application of derivatives. In the last few classes, we have discussed, other topics belongs to application of derivatives. So this is the last topic of application of derivative, and we are about to start this one. Before I proceed, I just like to confirm from a couple of you that you are able to hear my voice very clearly and able to view the screen properly. Could you please confirm, couple of you?
Yes,
Should I... Okay, great. Thanks for the confirmation. So let us start. Maxima minima. Now, to get a feeling about the purpose of finding the maximum and minimum of a function, let us consider the following practical problem statement. Okay, so let me tell you some of the practical problem statement, which will help you to understand that why we should, learn maxima minima, and you will find it is very important. Okay, so the first one is that, suppose the profit from a coconut grove is given by px equal to ax square plus ax plus bx square. The profit function px is equal to ax plus bx square, where a, b are real constants and x is the number of coconut trees per acre. That means per acre, if x is the number of coconut trees, then the profit is defined by ax plus bx square, where a and b are real constants. That means they are real numbers. Assuming each coconut tree gives equal number of coconuts, how many trees per acre will maximize the profit by selling coconuts? That is one case, one kind of example, okay, where the maxima and minima can help us to find the answer. Let's take the second one. A ball, when thrown into the air from a building 100 meters high, travels along a path given by the function, hx equal to, hx equal to 100 plus x minus x square by 100, where x is the horizontal distance from the building and hx is the height of the ball. Okay. Now the question is that what is the maximum height the ball will reach? Okay, so this is the second example where it is important to have the maxima minima to answer this question. Let's take the third example. A soldier placed at the coordinates 2, 3. That means if you have the Cartesian coordinate system of a battlefield, then a soldier is there at the point 2, 3. And that soldier wants to shoot an enemy helicopter traversing along the path fx equal to 3x square plus 5. When it is nearest to him, then so that it is there is no chance of missing the target. If this is a problem statement, the question is that what is the nearest distance between the soldier and the helicopter? So if you see, dear students, so I just took 3 examples from 3 different fields. And to answer these questions, the maxima and minima will going to help you a lot. That means what? Differential calculus has very effective application to find maximum and minimum values of any function. Here we will discuss function of one variable. Okay, as functions of 2 or more variable is beyond the scope of our discussion at this moment. Okay, so this is what we are going to discuss now. I hope by this time you all got a very clear idea that what is the motivation behind learning maxima and minima. Now, before we proceed further, we need to understand that what is absolute maximum and absolute minimum of functions of single variable. So our next point of discussion, dear students, is the absolute maximum and absolute minimum of functions of single variable, and that I'm going to discuss now in the next page. So to define that one, dear students, that first and foremost thing what I would like to say is that let fx be a real valued function of single variable x defined over a certain domain of definition, say D. Let me show you this thing and then you will understand. So let me copy paste this study material and let me explain from here. So what is the statement, dear students? Let fx be a real valued function of single variable x defined over a certain domain of definition, say D. That means what? Fx, that x, the argument of that function, will take a real number, and fx, the value returned by the function, is also a real number. And where it is defined? It is defined over a domain called D. D is the domain of definition. Now the function fx is said to have a maximum or absolute maximum value. Now the function fx is said to have a maximum or absolute maximum value at a point alpha belongs to the domain of definition D if and only if, that is IFF, fx is less than equal to f alpha for all x belongs to D. Okay, and we say f alpha is the maximum or absolute maximum value of f over its domain of definition D. Let me repeat one more, that fx is a function which will have a maximum or absolute maximum. Okay, why absolute maximum? Because we are studying the entire domain D, means where the function is defined. If we find that that fx is always less than equal to f alpha, okay, for all x belongs to D, and we say that f alpha is the maximum or absolute maximum value of f over its domain of definition D. In the similar manner, dear students, the function fx is said to have a minimum or absolute minimum value at a point beta belongs to D. D is the domain of definition if and only if fx is greater than equal to a beta for all x belongs to D. And we say a beta is the minimum or absolute minimum value of f over its domain of definition D. Dear students, after some time, I'll give you a graphical explanation about that absolute maximum and absolute minimum. When I'm going to give it? Because the next topic is that local maximum and local minimum. Once we discuss this thing, then I'll give you a graphical representation. So when it is either maximum or minimum, then we say it is an extremum. What is that? The function fx is said to be, the function fx is said to have an extreme value in D if there exists a point gamma belongs to D, okay, such that f gamma is either maximum value or a minimum value of fx in D. The number f gamma in this case is called an extreme value of f over its domain of definition D, and the point gamma is called an extreme point. Correct, dear students? So this is what is called an absolute maxima and absolute minima. Okay. Now, the next point what we are going to discuss, dear students, is that it is called the local maxima and local minima of a function of a single variable. Okay. What is that? Let us discuss. For the local maxima and local minima, so let me place this point first, and let me explain it in the next page. Sorry. So dear students, if you see this particular portion what I bring from our study material, that let fx be a real valued function of single variable x defined over a domain of definition D. Now, the function fx is said to have a local maxima at a point alpha belongs to D if there exists an open interval a comma b containing the point alpha, that means alpha is in between a and b, such that fx is less than equal to f alpha for all x belongs to a comma b open interval. Then we say it is a local maxima. In the similar manner, dear students, the function fx is said to have a local minima at a point beta belongs to D if and only if there exists an open interval a comma b containing the point beta, that is a less than equal to beta less than equal to b, such that fx is greater than equal to f beta. Now, dear students, few minutes back we discussed about the absolute maximum or maximum and absolute minimum or minimum, and now we are discussing local maximum and local minimum. Now let us understand by means of a graphical representation so that things will be amply clear. Now for that, first let me draw the coordinate axis. So dear students, so let's take, this is the y-axis and this is x-axis. Now we have a function, the function I am drawing something like this. Suppose this is the function. What is the function, dear students? This function is y equal to fx. And if you see what is its domain of definition, domain of definition is starting from the point here to this point here. That is the domain of definition. That means if we assume this entire set, suppose, if we say this is capital A and this is capital B. So in the closed interval capital A to capital B, that is called the domain of definition. Now, dear students, if you look into it, in this particular domain, what we get is that, what is the absolute maximum? Without having knowledge of that, in a differential calculus, you can say, sir, where is the absolute maxima? We can say the absolute maxima is this point, correct? And where is the absolute minima? Absolute minima is this point, correct, dear students? So these 2 points, what I marked in the green color, are the absolute maxima and absolute minima. Because, and that is what is called either maximum or minimum. So this is called the maximum or absolute maximum, maxima, and this is called the minima or absolute minimum. Correct? Now, what is local maximum and local minimum? Then local maximum and local minimum, dear students, what happened? It is based on a point. Okay, as you see the definition above, it is given that the function fx is said to have a local maximum at a point alpha belongs to D if there exists an open interval a comma b containing the point alpha, that is a less than equal to alpha less than equal to b, such that fx is less than equal to f alpha for all x belongs to a comma b. Whatever I said, dear students, let me give you the visual representation. Already you are able to see the graph. So suppose we take a point, we take a point, suppose I take this point using this color, okay? Suppose we take a point here. This point we are taking. Now, this is particular point. Now, surrounding this point, if we find 2 values a and b, okay? Suppose we take, surrounding this point, that alpha, we get the point a and b. Okay, suppose this is the point A, this is the point B, and this is the point, alpha. So this is the point alpha. Then in this interval A to B, in the open interval, wherever the maxima and minima, that we call it as a local maxima. So what is the local maxima here, dear students? This is the local maxima. And so let me draw it in, mark it in a different color. Suppose I mark it in this color. Yeah. So this is the local maxima and this is the local minima. Correct? So what we see, dear students, here, that is local maxima. So let me mark it. As you see here, so this is local maxima. And this is local minima. So dear students, so in simple terms, by absolute maxima is known as maxima and absolute minima is known as minima. So what is absolute maxima and absolute minima? It is the minimum most value and maximum most value in the entire domain of definition of the function. And what is local maxima and local minima? Local maxima and local minima is on a, in a portion of this entire domain of definition. It is surrounded by a point alpha, as I said few minutes back. So now what we understood this, though we can explain that local maxima and local minima in a in different manner as well. On the other hand, what we can give the following formal definition. Okay, what is the definition? What we can say is that so let me first place this note and then let me explain you. As you see, dear students, on the other hand, we can give the following formal definition. Let fx be a real valued function and let C be an interior point in the domain of fx. Then the point C is called a point of local maxima if there is an h greater than 0 such that fc is greater than equal to fx for all x belongs to the open interval c minus h to c plus h. The value fc is called the local maxima value of fx. Now geometrically, the above definition states that if x equal to c is a point of local maxima of fx, then the graph of fx around c should be something like this. This is one very important graph, dear students, here. So if you see, this is the graph it should be. What does it mean? That at the point f dash c, what is f dash c? From the tangent and normal, if you remember, that is nothing but the slope of the tangent. So if this is the point C, then what we are going to get? This is the point C, na? Then what is the slope of the tangent at that point C? That is f dash c should be equal to 0, right? Because f dash c is actually horizontal. That is the tangent is horizontal to the x-axis. So f dash c is equal to 0. Now left hand side of it, what we see, if I draw in a different color, dear students, that left hand side of C, if I draw in blue color, so this is the function is increasing in the left of C. That is why f dash x is greater than 0. Dear students, if you remember monotonicity, we discussed in one of our previous session. If f dash x is greater than 0, that means the function is increasing. And the right side of C, if I draw it in the green color, if you see this portion of the graph, here what we see is that f dash x is less than 0. That means the function is decreasing. I would like to explain you in little, in details here. So let me draw the graph once more. Okay. So suppose this is the graph. Let me draw the graph. So suppose this is the graph. That is the graph y equal to fx. So now in this surrounding this point, suppose this is the point C. Now in this point C, what happened is that why it is local maxima? Because left of that point C, left of this point actually, you see that the function is actually increasing, because as x is increasing, the function is also increasing, correct or not? And in the right hand side of this point, what we see, the function is decreasing, correct? So that is why it is called a maximum point, local maxima. Local with respect to what? Always local means surrounded by a point. Here the point is C. So how it happens, dear students? So if you draw a tangent, this tangent is actually parallel to the x-axis. Now, what is the slope of the tangent? That is the differentiation of the function at that particular point. As this is the point C, then what is that slope of the tangent? It should be f dash c. Now, what we see, that slope, that inclination is 0 degree with the x-axis. That means what will be tan 0? That is the slope is 0. So that is why f dash c is equal to 0. Now left of it is actually increasing, dear students. So how you know it is increasing? There are two ways. By inspection you are able to see the left of it is actually increasing. If I draw this in the blue color, if you see the left of it is actually increasing, correct? There are two ways you can signify it is increasing. One is that, suppose, let me draw only once, is that, if you take any point in that portion of the curve, what I draw in the blue color, if you take any point here, suppose you take this point and you draw a tangent to this point. Okay, if you draw a tangent at this point, so what you will get, dear students? You will see the tangent is actually makes an acute angle with the positive direction of x-axis, isn't it? So suppose if you extend that one, then what will happen? You will see that angle, what it is making with the positive direction of x-axis, the positive direction of x-axis, if you extend that one, that is actually acute angle, and tan of acute is always positive. That is why f dash x is positive. That is why f dash x is greater than 0. F dash x greater than 0 means what, dear students? From the increasing function and decreasing function, it's the function is increasing. That is why here it is written it is increasing. Now let's look. There are two ways we are looking into the same scenario. That as the tangent at any point where the function is increasing, if we draw the tangent at any point to that portion of the curve, that tangent is making an acute angle with the positive direction of x-axis. Hence it is, as tan of that acute angle is positive, that means f dash x is positive. Hence the function is increasing. That is one way of looking into it. Another way of looking into it is a very straightforward, because I'm able to view the curve of that function, and the visual representation is given to me. From there actually I'm able to see that in the blue portion of the curve it is increasing. In the similar manner, dear students, if I take the right side of C in the green color, so this is the portion of this function. And if you take any point here, and draw a tangent to this at this point, what you will see, dear students, you will see that it makes an angle. So if we, increase that x-axis like this, what you see? You see this angle is actually obtuse angle, correct or not? And tan of an obtuse angle is what? Tan of an obtuse angle is negative. That is why what we can say? We say f dash x is less than 0. Now f dash x is less than 0, from the knowledge of our monotonicity, what we know? It is a decreasing function. That is why it is written as decreasing. So if you understand that particular point very clearly, dear students, now let me revisit the statement what I said, is that, the point C is called a point of local maxima if there exists an h greater than 0 such that fc is greater than equal to fx for all x belongs to the open interval c minus h, c plus h. The value fc is called the local maximum value of fx. Geometrically, the above definition states that if x equal to c is a point of local maxima of fx, then the graph of fx around the point C will looks like whatever you see, and I also described few minutes back. And if you notice this particular statement here, it is to be noted that the function fx is increasing, that is f dash x is greater than 0 in the interval c minus h to c, which is the blue portion of the curve. And the function is decreasing, that is f dash x is less than 0 in the interval c to c plus h, which is the green portion of the curve. And now if at some portion it is increasing, some portion it is decreasing, then in the midpoint it has to be 0. Otherwise how a function can from increasing, how it can decrease? Means what I wanted to mean is that if a function start increasing and after that it has to decrease, then it has to go like this, then only it is decreasing, right? So that means you get a point here where it is neither increasing nor decreasing. That is what is f dash c is equal to 0. That is what is actually mentioned by this point, dear students. I hope you got a clear idea about that what is meant by the local maxima. Correct, dear students? In the similar manner, we can define the local minima as well. We just discussed, local maxima. Similarly, we can define the local minima. How we can define the local minima? Let me explain you. Let me first take the portions of the study material and then let me show you. After that, I will explain you in details. Okay, dear students? So, the point C is called a point of local minima if there exists an h greater than 0 such that fc is less than equal to fx for all x belongs to the open interval c minus h comma c plus h. The value fc is called local minimum value of x. Let us give a visual representation of this particular statement, whatever I said. Okay, it is just like whatever we discussed about the local maxima. It is similar to it. So what is that? If you look into this one, so if you look into this particular graphical view, geometrically, the above definition, what I defined for the local minima is states that if x equal to c is a point of local minimum of fx, then the graph fx around c will be something like this. As you see here, something like this. Correct? That means in the left of that point C, the function is actually decreasing. Exactly opposite to the local maxima case. That means if I draw the left part of the point C is in the blue color. If you see here, as you see, as x is increasing, fx is decreasing. That means it is a decreasing function. And if you see the right side of C, if I draw it in the green color, it is actually increasing. Increasing means f dash x is greater than 0. Decreasing means f dash x is less than 0. We already discussed this point. So the but curve will looks like something. And at that point, at that point of C, what we'll get is that f dash c is equal to 0. So a decreasing function looks like something like this. So if this is your function y equal to fx, so what we find is the local minima is this point. Correct? So here to be noted that the function fx is decreasing, that is f dash x is less than 0 in the interval c minus h comma c, and increasing, that is f dash x is greater than 0 in the interval c to c plus h. This suggests that f dash c is equal to 0 in the similar manner. Dear students, I hope you got it. Clear? Now, so as we have just discussing about that local maxima and local minima, I would like to tell you one important point. And before mentioning this important point, let me just show you the let's just give you the particular portion from the study material, and then let me explain it. What is that? Here it is to be noted the following point. Let fx be a function, okay, defined on an open interval I. Suppose C belongs to I, that means C is an element in that open interval I, be any point. Now if fx has a local maxima or local minima at x equal to C, then either f dash C is equal to 0 or fx is not differentiable at C. That is, f dash C does not exist. I repeat, dear students, very important statement. Let fx be a function defined on an open interval I. Suppose C belongs to I. That means C is an element in the set I, which is an open interval. Okay. Now, if fx has a local maxima or local minima at x equal to C, then either f dash C has to be equal to 0, whatever we have seen in the previous two cases, or fx is not differentiable at x equal to C. That is, f dash C does not exist. But the converse of the statement is not necessarily to be true. That means if f dash C is equal to 0 or fx is not differentiable at C, that means f dash C does not exist. That doesn't necessarily mean that function fx has a local maxima or a local minimum at x equal to C. Let's take an example. If we take the function of fx equal to x cube, and what we'll see, f dash x is equal to 3x square, and we see f dash 0 is equal to 0, but x equal to 0 is neither a point of local minimum nor a point of local maximum, as we observe from the following diagram. You see this particular point x equal to 0. Can you say by looking into the function whether it is a minimum or maximum? No, but still f dash x equal to 0. So if the function is having a local maxima or local minima, then f dash C has to be 0 or f dash C has to be not defined. That is, f dash C does not exist. But the converse is not true. That means what? If f dash C is equal to 0, okay, or fx is not differentiable at C, that means f dash C does not exist. That doesn't necessarily mean that the function fx has a local maxima or local minima at x equal to C. One example is evident here, fx equal to x cube. If you differentiate fx equal to x cube, f dash s becomes 3x square, and at the point 0, you get f dash 0 is equal to 0. So now at 0, we see from the graphical representation, the function neither have a maximum value nor have a minimum value, despite having f dash 0 equal to 0. So it proves that the converse is not true. Correct? This is a very important observation. Now, as we just conclude that the point about the local maxima and local minima, I'd like to say you few points, very important points. Okay, I'm going to discuss those points one by one, dear students. Okay, so the first points to remember. So the first point, what I can say is that, and it's a very important point. You should take a note of it. So let me explain all these points one by one in the next page. The first point is that following are some key points regarding absolute maximum, absolute minimum, and local maximum, local minimum. Point number 1. A function may have multiple local maximum or multiple local minimum over the domain of definition of the function. How? Let me show you by means of an example. That let me first draw the coordinate axis. Okay, suppose the function, so graphical representation of the function, let me draw something like this. Suppose this is the function y equal to fx. If you see, this function has multiple local minima and multiple local maxima. How? If you consider this particular interval, okay, you will find this is the maximum, this is the minimum. If you consider this particular interval, you will find this is the maximum and this is the minimum, like this. So that actually states that a function may have multiple local maxima and or multiple local minima over the domain of definition of the function. Correct, dear students? Now let me proceed for the next statement, next point actually. The next point says that, for a function, let me first, note it down and then let me explain. Okay. Let me first place that, particular note from the study material. By the way, dear students, all the study material available in the online platform at konarclasses.com for your reading purpose. Okay. So what it says is that, for a function, it may be possible to its local minima value is more than the local maximum value over the domain of definition of the function. Very interesting point. I repeat, for a function, it may be possible of its local minima value is more than its local maximum value over the domain of definition of the function. Let us understand how come that local minima is more than local maxima. Maxima means more. So how come local minima could be more than local maxima? It looks like a kind of a contradicting statement, but not really, dear students. Let's take an example and understand. Let us understand both the above point number 1 and point number 2, whatever I discussed, by means of an example fx equal to x square. If you recall, dear students, from your previous year knowledge, fx equal to x square represents the equation of a parabola. And if we give the graphical representation of parabola, it's look like this. Let me place it here, dear students. So what will be the graphical representation of parabola? It will be something like this. So let us now observe. So this is the equation of fx equal to x square, or we can write that is equal to y equal to x square, the equation of the parabola. If we observe the following points, dear students, in the interval -2 to 3, okay, in the interval -2 to 3, the minimum and maximum of the function are -2 whole square and 3 square, that is 4 and 9 respectively. So -2 to 3. So if I draw a line here, -2 and 3, correct? From -2 to 3, what is the minimum and maximum of the function? That is 4 and 9. So this is the value 4. This value, you see, this value is 4, and this value is 4, by the way, and this value is 9, correct? And in the interval 0 to 1, okay, the minimum and maximum value of the functions are 0 square and 1 square, that is 0 and 1 respectively. So we observe that the function fx equal to x square has multiple local minima and multiple local maxima over the domain of definition. So if you look into 0 to 1, so what we see, this is the minimum value, this is the maximum value. In the interval -2 to 3, we see this is the minimum value, this is the maximum value, correct? So these are the different points. So again, I say once more, in the interval -2 to 3, so minimum value is suppose m1 and maximum. So minimum and maximum both starts with m. Suppose we see it is that min 1 and it is max 1. And here this point is min 2 and this point is max 2. So what it says, that we observe that the function fx equal to x square is having multiple local maximum and multiple local minimum values over the domain of definition of the function. The local minimum value of fx equal to x square in the interval -2 to 3 is 4, and local maximum value of fx equal to x square in the interval 0, 1 is 1. So you observe that the local minimum value of fx equal to x square in the interval -2, 3, which is 4, is more than the local maximum value of fx equal to x square in the interval 0 and 1. So what it says, dear students, if I use a different color, that means in the interval, sorry, in the interval -2 to 3, what we see the minimum value, that is 4, is actually maximum than the more than the local maximum value in the interval 0 to 1, which is 1. Correct? So that's actually state whatever I said in few minutes back. It is possible to have the local minima is actually more than the local maxima in the entire domain of definition. Correct, dear students? Now let us look into the point number 3. The point number 3, dear students, let me first place this statement, and followed by let me explain it. So point number 3 says, dear students, that every monotonic function assumes its maximum and minimum value at the endpoints of the domain of definition of the function. In general, we see that every continuous function on a closed interval has a maximum and a minimum value. Let us understand the above point, whatever I just said, by means of an example, so that it will be more clear. Let us consider the function fx equal to x. What is that function fx equal to x, dear students? It is nothing but a straight line passing through origin, and actually, in fact, you can say it is a bisector of the coordinate axis, right? Now, the maximum and minimum value of this function depends on the domain of definition of the function fx. If the domain of definition of the function open interval 0, 1, then we can represent the function graphically as like this, whatever you see in here. This is the point 0, this is the point 1. So this is the way we are defining the function graphically. Correct, dear students? Now let me bring the next point, next statement of this point, so that we can understand it very clearly. Now let me first place the statement, and then let me followed by its explanation. If you see, dear students, the given function, whatever you see fx equal to x, is an increasing function in the given interval 0 to 1. From the above diagram of the function fx, it seems that it should have the minimum value at a point closer to 0 on its right, but no such point is possible to find in abstract manner. If not, let us assume x0 be the point closest to 0 on the right. Now we can find a point x0 by 2 which is less than x0, closest to 0 on its right, which is contradict to the fact that x0 is the point closest to 0 on its right. And from the above diagram of the function fx, it seems that it should have the value at a point closest to 1 on its left. Correct? But no such point is possible to find in abstract manner. You can definitely say that this is the point. Why? Because if we assume that x1 is the point closest to 1 on its left, then we can always find another point x1 plus 1 by 2 which is more than x1 and closer to 1 on its left, which is contradict to the fact that x1 is the point closest to 1 on its left. Correct now? So why I'm saying so, dear students? This statement says that that if the domain of the definition of the function is not open interval, if it is a closed interval, we can find the minimum value of the function fx equal to fx is at x equal to 0, which is 0, and we can find the maximum value of fx at x equal to 1, and that is 1. Correct, dear students? So what I wanted to mean, but if the domain of definition is the closed interval 0, 1, we can find the minimum value of the function fx at x equal to 0 and is 0. Also, we can find the maximum value of the function fx at x equal to 1 is 1 when the domain of definition is the closed interval. But when the domain of definition is the open interval, what has been showed by means of this diagram, if you see the extreme point 0 and 1 is actually unfilled circle. Unfilled circle symbolized to open interval. There we see that whatever the statement I mentioned is that you cannot say in an abstract manner that what is the maximum and minimum. Correct, dear students? So I hope you understood this particular point very carefully. Okay. Now, what we are going to discuss is that, the first derivative test to find local maxima, local minima of function of single variable. Okay. And this is very, very important. Whatever I have discussed, that next 2 points will be very important. That is the first derivative test, and second one is what we are going to discuss is the second derivative test. Extremely important. Whatever I have discussed so far, just to give you a very clear idea about what is local maxima, what is local minima, what is absolute maxima, what is absolute minima, and different corner cases. Okay. Now, what we are going to discuss is that which is the most important, and it's also important to solve physics numerical problems as well, dear students. The first one, what I'm going to discuss is the the first derivative test to find local maxima, local minima of functions of single variable. Let me first place the the notes from the study material, and then let me explain you. Okay, so let fx be a function defined on an open interval I. Let fx be continuous at a critical point C belongs to I. If f dash x changes its sign from positive to negative as x increases through C, that is, if f dash x is greater than 0 at every point sufficiently close to the point C but left of C, and f dash x is less than 0 at every point sufficiently close to and to the right to C, then we can say that C is the point of local maxima. That means what? If I give you a graphical representation of this particular thing, is that it is something like this. Let me give a graphical representation of this one, particular one. Okay. It says that, let me draw the graph in a different color. That, okay, if you see that fx, if f dash x changes its sign from positive to negative, okay, as x increases through C. So this is the point C. So from left hand side, if you see, it is actually f dash x is greater than 0, and it is changing its sign. So in this region, f dash x is greater than 0. After the point C, it is actually changing its sign. That is, here we see that f dash x is less than 0. Correct? If f dash x, now let me revisit the statements once more. If f dash x changes sign from positive to negative as x increases through C, that is, if f dash x is greater than 0 at every point sufficiently close to and to the left of C, and f dash x is less than 0 for every point sufficiently close to and to the right of C, then C is a point of local maxima. Now let us understand what is meant by the second statement. So this is what we discussed about the first statement. Now the second statement says that if f dash x changes sign from negative to positive as x increases through C, and f dash x is less than 0 at every point sufficiently close to and to the left of C, and f dash x is greater than 0 at every point sufficiently close to and to the right of C, then C is a point of local minima. Dear students, whatever I said in the last few seconds, let me give you a visual representation. Let me give you a visual representation so that you have a very clear understanding. Let me draw this curve in green color. Okay, so this is the function fx, and here is the point C. Now let me revisit the statement, this statement, that if fx changes its sign from negative to positive as x increases through the C, so this is C. So here f dash x is less than 0. Here f dash x is less than 0 at every point sufficiently close to C and to the left of C, and f dash x is greater than 0 at every point sufficiently close to and to the right of C. That means here we get what? F dash x is greater than 0 at every point sufficiently close to and to the right of C, then C is a point of local minima. Now, whatever I said, if you just have a visual representation of the green color curve and the blue color curve, you can clearly visible that which one is the local minima and local maxima. Obviously, for the blue color curve, you see that C is the point of local maxima, and for the green color curve, what we see is that C is the point of local minima. Now, the third point, dear students, is that if f dash x does not change sign as x increases through C, then C is neither is a point of local maxima nor is a point of local minima. In fact, such a point is called a point of inflection. Let me repeat once more, dear students. If f dash x does not change sign as x increases through C, then C is neither a point of local maxima nor a point of local minima. In fact, such a point is called the point of inflection. Okay? If there is no change of sign in f dash x, then you cannot bend that curve, no? Geometrically, if you see. If you see the blue color curve and the green color curve, in both the curve is actually bent at the point C. The point where it bends, that is the point of local maxima or local minimum, depending on that how the f dash is actually changing. If f dash x is changing from positive to negative, then that point C is called the local maxima, which is the represented in the blue color curve. But if you see that f dash s was less than 0 and from negative it turned to positive, which is there in the represented in the green color curve, you see that C is a point of local minimum. But if you see that f dash x is not changing its sign at all, it is consistently greater than 0 or consistently less than 0, then you cannot find that, you cannot say that C is neither a point of local maxima or local minima. In fact, such a point is called a point of inflection, dear students. I hope it is clear about that, the first derivative test. Now, what is the most important? I repeat, most important is called the second derivative test. Okay, and that I am going to discuss now, the second derivative test, and that I am going to discuss in the the next page. Very important. Every year I see that questions come, where you need to apply the concept of second derivative test, and this is very important. Okay, dear students, so let me start. It is called the second derivative test to find local maxima, local minima of function of single variable. So to start with, let fx be a real valued function. Let me first, write down the notes here, and then followed by, let me explain. Let fx be a real valued function of single variable x defined over an interval I. Also, let the function fx is differentiable over the interval I as well. Now, following are the steps to be find the value of x at which fx possesses either maximum value or minimum value. Step by step, dear students. Notice these steps very carefully. The step one, step one is that assign y equal to fx. So let me first, place this point, dear students. Okay, and then let me explain it. Okay, the first step, very important, dear students. First step is that assign y equal to fx. Okay, let me use a different color. Assign y equal to fx. Second one is that find the first order differentiation of fx, that is dy dx, that is f dash x. Then assign the third step, assign dy dx equal to 0, that is f dash x equal to 0. F dash x equal to 0 is what? Is an equation. So let us solve it for x. That means find the values of x so that f dash x equal to 0, that is dy dx equal to 0. Please note all these values of x, and these are the critical points. That means why critical points? Because these are the points for which the value of f dash x equal to 0. That means all those points, if you draw a tangent to the curve, the tangent is actually should be parallel to the x-axis. A different way of viewing this same statement. So these are all the critical points of the function fx. Now let's come to the fourth step. That is find d2y dx2, that is f double dash x. Done. Now let's come to the fifth step. F double dash x, you understand, that is equal to nothing but d dx of f dash x. Okay, that is what is known as f double dash x. Now the fifth step is very important. All the steps are important. So if you miss one step, it will not work. Fifth step says that for each value of x, that is alpha, what you obtained in the above step 3, that is for dy dx equal to 0, that is by solving that equation you got different values of x. Now let's take one such value is x is alpha. For each value of x, means here you take one value is alpha. As obtained in the above step 3, we find the value of d2y dx2 at x equal to alpha, or we can say it is f double dash alpha. And we conclude the following. If we see that d2y dx2 at x equal to alpha is greater than 0, that is, if f double dash alpha is greater than 0, then we say the function fx has minimum value at x equal to alpha, and the corresponding minimum value is f alpha. On the other hand, if we find that d2y dx2 at x equal to alpha is less than 0, that is f double dash alpha is less than 0, then we say the function fx has maximum value at x equal to alpha, and the corresponding maximum value is f alpha. Now it may be possible that d2y dx2 at x equal to alpha is equal to 0. That means it is neither greater than 0 nor less than 0. That is, it is equal to 0. That means f double dash alpha is equal to 0. Then no conclusion can be made about the maximum or minimum value of fx and alpha at alpha, and we needs further investigation. Correct, dear students? So I hope these statements are very well understood to you. Now, what we see is that the last point is that is this, we found it out what is the maximum value and minimum value. Now the sixth step, what I can say is that it is something like this. We assume that the function fx is differentiable, over the interval I. But in case the function fx is not differentiable at a particular point beta, say, belongs to I, then we say that the function fx has no maximum or minimum value at the point beta. Okay, so the point 6 is not that important because, our assumption is that the function is differentiable. But if we find that in a particular point of the interval, if the function is not differentiable, then we can say, the function, has no maximum or minimum value at that point beta. Correct, dear students? Now, whatever we discussed about the second derivative test to find the local maxima and local minima. As you see here, to find the local maxima or local minima of a functions of single variable. Now, the last point what we are going to discuss is that to find the absolute maxima and absolute minima of a single variable. After that, we will solve one representative problem to have our understanding absolute clear. Okay, dear students. So the next point what I'm going to discuss here is the, a note on finding absolute maxima, absolute minima of function of single variable. Okay. So steps are very straightforward and simple. So let me first, write down the steps and then let me explain you. Okay. So let fx be a real valued function of single variable x defined over a closed interval I. Also, let the function fx is differentiable over the open interval I. Now, to find the absolute maxima, absolute minima of the function fx, we should follow the step mentioned below. The first step, find the local minima, local maxima of the function. Okay, as we discussed in the previous steps using the second derivative method. Okay. Now the second step is that find the value of the function at the end points, because it is a closed interval, because the function is defined in the closed interval I. So there will be extreme points. So suppose if the closed interval I is a comma b, then you should find the value of the function at fa, at a, that is fa, and value of the function at b, that is fb. Correct? Value of the function at b. So let me write it down here. The value of the function at the point b, that is fb. Now, so in this step, first step, you found all the local maxima and local minima points and the value of the function on those points. Those are the local minimum value, local maximum value. And in the second step, we are finding the value of the function at that extreme steps. Why? Why you are not able to find due to local minima or local maxima? Because our domain of definition says that the function is differentiable in the open interval I. Fx is differentiable over the open interval I. That is why we are not able to find the maxima and minima by means of the first order derivative using that at the point a and b. Better to find the absolute value, better to find the value of the function at the extreme points a and b. Then comes the third step. It is nothing but comparing all the values of the function obtained in the above two steps. That is step 1, finding the local maxima, local minima, and step 2, the value of the function at the extreme points. The greatest value among all these values will be the absolute maximum value of the function, and the least value among all these values will be the absolute minimum value of the function. So I hope, dear students, you understood how to find the absolute maxima and absolute minimum of functions of single variable. Now, dear students, the last point what I'm going to do is that let's solve a problem together. Okay, so I suggest you please open your notebook and we are going to solve one question together. And that is, this question also very important. is few years I saw it came in the exam as well. So the question here is that, the find the maximum and minimum value of the function 1 by x power x when x is greater than 0. Let us solve this. So what is the first step, dear students? Follow my statement very carefully. First step is that we will write y equal to 1 by x power x. That is the first step. Now, as y equal to 1 by x power x, from here what we can say, dear students? From here we can say log y is equal to log of 1 by x power x, log of 1 by x power x. That implies log y is equal to x log 1 by x. Correct, dear students? That implies log y is equal to x into log of m by n, that is log m minus log n, that is log 1 minus log x. What is the value of log 1? Log 1 value is 0. So from here what we can say, dear students? That log y is equal to x into 0 minus log x. Correct? So that implies what we get is that log y is equal to minus x log x. Correct, dear students? Now what we need to do, we need to find dy dx. To find dy dx, we need to differentiate both sides with respect to x. So this implies what? d dx of log y should be equal to minus of d dx of x log x. Correct, dear students? So this implies what? For the left hand side differentiation, we need to apply the chain rule. That means what? It should be d dy of log y. Why so? Because log y is a function of y. So first we should differentiate with respect to y, then dy dx. And minus, what we can find is that d dx of u into v, that is u into d dx of v, that is d dx of log x, plus log x into d dx of x. Correct, dear students? So from here what we get, d dy of log y is 1 by y into dy dx. Then what we are going to get? Minus what we get, x into d dx of log x is 1 by x plus log x into d dx of x is 1. So from here what we get, dear students? From here we get dy dx is equal to minus y into 1 plus log x. Correct? Why you are able to do it? Since x is not equal to 0. Correct? So now that is the first order differentiation, that is dy dx is equal to minus y into 1 plus log x. Now, dear students, we need to make second order differentiation. To find the second order differentiation, what do you need to do? We need to find d2y dx2. So let's find d2y dx2. So this implies d2y dx2 is equal to, that is minus of d dx into y into 1 plus log x. Correct, dear students? So this is equal to what? Minus of y into d dx of 1 plus log x. Correct? Plus 1 plus log x into d dx of y, that is nothing but dy dx. Correct, dear students? So now from here what we are going to get, if we simplify further, so from here what we are going to get is that d2y dx2 is equal to minus of y into ddx of 1 plus log x is ddx of 1 is 0 and log x is 1 by x. So that is y into 1 plus x plus 1 plus log x into dy dx. dy dx is equal to, minus y into 1 plus log x. So what we are going to get is that minus y. So dy dx. So what we are going to get is that here minus y into 1 plus log x complete whole square, because the value of dy dx is actually minus y of 1 plus log x, which we are applying here in this value here. Then become what? Minus y into 1 plus log x whole square. Correct? So this we find the value of d2y dx2. So we can write here is that d2y dx2 is equal to minus of y by x minus y into 1 plus log x whole square. So this is the value of d2y dx2. Now dear students, for the maximum or minimum value, what you need to do? We need to have dy dx equal to 0. So if we apply dy dx equal to 0, what we are going to get out of it? Dy dx equal to 0 stands for, minus y into 1 plus log x equal to 0. Correct, dear students? So now, that means 1 plus log x equal to 0. This implies 1 plus log x equal to 0, since y cannot be equal to 0. Y cannot be equal to 0 as x is not equal to 0, because y is equal to what? Y is equal to 1 by x power x, as x is greater than 0, not equal to 0, x is greater than 0 according to the given condition. So y, which is equal to 1 by x power x, cannot be equal to 0. So 1 plus log x equal to 0. 1 plus log x equal to 0 means what, dear students? That means log x equal to minus 1. That means what? From here what you can say? X is equal to e power minus 1. That implies what we get? The value of x is equal to 1 by e. Now at x equal to 1 by e, whether the function is having maximum value or minimum value, for that what you need to do? We need to find the value of d2y dx2 at x equal to 1 by e. Okay. So then what we find is that, dear students, so we find d2y dx2 at the value at x is equal to 1 by e. What we are going to find that value, dear students? So minus y by x. So what we are going to get is that if we find the value of d2y dx2 at x equal to 1 by e, so what we are going to get? Minus of y. Y is what? It is 1 by x power 1 by x power x. So that means e power 1 by e into 1 by x, that is e. Correct? So and so minus, let me write it down here. Okay, what is y? Y is equal to 1 by x power x. So let me find the value in this different color, dear students. So from here, if we find the value, so it becomes minus, what is this value? Y is equal to 1 by x power x. From where we are getting? We are getting from here. 1 by x power x is given in the definition. That's what we assume. And then into 1 by x, okay, minus y y is again minus 1 by x power x into 1 plus log x into 1 plus log x whole square. That is the value. So now for this value, if we apply x is equal to 1 by e, so it should be minus of e power 1 by e into 1 by x is e minus 1 by x is actually e power 1 by e into 1 plus log x. 1 plus log x is 0. How? Because from here we can say 1 plus log x equal to 0 at x equal to 1 by e. So ultimately you will get it 0. Correct? So in fact it is not required to give a second bracket. We can easily do it in the first bracket, dear students. Correct? So what we are going to get from here? So we see that the value of d2y dx2 at x equal to 1 by e is actually minus e into e power 1 by e, which is less than 0. So what we can conclude? We conclude that at x equal to 1 by e, the function has maximum value. So from here what we can say is that at x equal to 1 by e, the function that is 1 by x power x has maximum value. And what is the maximum value? And the maximum value is maximum value is instead of x we'll write 1 by e, so 1 by x become e power x means e power 1 by e. So e power 1 by e is the maximum value of the function 1 by x power x, which is attained at x equal to 1 by e. Now dear students, we see that we didn't find any value of x for which d2y dx2 is greater than 0. So what we can say? We can say the function 1 by x power x does not have any minimum value. So dear students, you get a fair amount of idea that how we can apply the second order derivatives to find the maximum and minimum value of this function. So the video recording of this entire session will be available in another 2 hours from now. You can have a look into all these things, look it repeatedly, and you will have a very clear idea about the maximum and minimum. So with this, I would like to conclude the class for here, dear students, and we will have our next class in day after tomorrow, and there we will discuss about the mean value theorem. Thank you very much.
Thank you, sir.
Thank you very much.
Thank you, sir.
Thank you. Take care.